Welcome to MOVITRAC LTP-B Basic and Intermediate Training. This is Session 3. In this session, we're going to tackle a very important and surprisingly complex topic, that of ramps. We're going to look at how the VFD can accelerate and decelerate. We're also going to look at the related topic of how it can stop under a variety of conditions. And then finally, we're going to unlock a lot of additional VFD power by accessing the extended parameter set. So much to cover, let's get started. Let's begin by talking about ramps. Ramps are an interesting topic. They're very important because they enable you to customize the VFD's behavior to your application, but they're also surprisingly sophisticated. So let's begin with the really obvious question, what is a ramp? A ramp is an acceleration or deceleration event, a period of time when the VFD is changing its speed either up or down. This is a diagram of a ramp, and I think you can see why we call them ramps because that's exactly what they look like. This diagram is a graph of speed versus time. The horizontal axis represents time going by, and the vertical axis represents the VFD's speed over that period of time. Now you can see if you look near the beginning of the graph that there's an acceleration ramp where the speed is increasing from 0 to a set point value. In the middle, it's not accelerating, it's operating at a steady speed for a period of time. And then at the end, we have a deceleration ramp where the speed drops down from that set point speed back to 0. You can see the ramps aren't the same. The acceleration ramp is shorter than the deceleration ramp, and that can certainly be true. Ramps don't have to be the same. The VFD allows you to set independent acceleration and deceleration ramps. We specify ramps in the VFD by setting parameters, and they are times equal to the time required to make a 50 Hz frequency change. Now that may seem a little odd to you because we think of acceleration and deceleration being associated with speed, but remember the VFD is controlling speed by controlling frequency. Now you may wonder, where does 50 Hz come from? Well, in European countries they typically use 50 Hz motors, and so a 50 Hz frequency is the maximum speed. So if you accelerate the VFD from a full stop, you go from 0 Hz to 50 Hz, and if you decelerate it, you go from 50 Hz down to 0. Now in the United States, of course, our motors tend to be 60 Hz, and so that is a little bit different. You will have to kind of make that mental adjustment, but I will give you an equation that actually makes dealing with ramps relatively simple. Now maybe you're thinking that I haven't really answered your question. Why are we expressing accelerations in terms of frequency change rather than speed change? Well, remember this. The motor's speed depends on the frequency and the number of poles in the motor. The same frequency produces different speed changes with motors with different numbers of poles. So by making the acceleration tied to frequency, we sort of make it independent of the number of poles in the motor. Now, of course, you need to know how many poles you have to know what kind of speed change you can expect to see. I think this will be a little clearer in just a few minutes. Let me add something to our diagram here, however. Let's add some times. All right, our first acceleration ramp takes 1 second. It goes from 0 to 50 Hz in a single second. Our deceleration ramp takes twice as long. It takes 2 seconds to come down from 50 Hz to 0 Hz. So if we're programming this ramp into our VFD, we would set our acceleration ramp to 1 second, and that would make our 50 Hz speed change take 1 second. We would set our deceleration ramp to 2 seconds, and that would make the deceleration ramp take twice as long. Do remember, however, the actual speed change depends upon the number of motor poles. And here's that equation again if you need to review it. So for example, let's say this is a 4-pole motor and we do this 50 Hz speed change. We can run this number through the equation and we'll find out that the speed at 50 Hz is 1500 RPM. So this acceleration ramp is going to cause the VFD to take 1 second to change its speed from a full stop to 1500 RPM, or it will take 2 seconds to decelerate that motor from 1500 RPM down to a full stop. I think that should make sense, but if not, maybe you want to watch this slide again. All right, now that's fine if you're doing 50 hertz speed changes, but what if you want some other kind of speed change, or what if you really don't even want to work with frequency at all? What if you want to work with RPM? Is there a solution to it? And the answer is absolutely. There's an equation here that I've put together, and this will tell you what you need to put into the parameter to get a desired acceleration for a speed change with a motor of a given number of poles. So let's define a few terms here, and then we'll work with this equation. First of all, you notice there's something called speed change in the equation. What is that? That is the number of RPMs that are going to change from the initial speed to the final speed. So to calculate the speed change, work out the speed you're going to start at, work out the speed you're going to wind up at, take the difference between them, take the absolute value so there's no negative sign, and that's the speed change. You can then plug that into the equation along with the motor poles and the acceleration time, and that will tell you what to plug into the parameter. Now, I better define acceleration time. It's simply the time for that speed change to occur. So that is what you want to happen. And then we'll get the ramp time out of that. That is the value that you actually insert into the ramp parameters. Okay, I think we need to do an example problem to sort of cement that in place. Let's take an example where we accelerate a 4-pole motor from 250 RPM, so it's already turning actually, to a higher speed, 1000 RPM, and we want this to take 3 seconds. So this is sort of a graph of what's going on. We're operating at 250 RPM, then we begin a speed change. We have an up ramp. We go up to 1000 RPM over a period of 3 seconds, so between 3 and 6 seconds this takes place. Then we steady out at 1000 RPM and continue to operate at that speed. Okay, that's what we're doing. So we need to calculate the speed change first. We take the final speed, we subtract the initial speed, we take the absolute value. So in this case, it's 1000 RPM minus 250 RPM. That equals 750 RPM, so that's our speed change. And then we plug it into this equation here. So we're going to put in 3 seconds in our acceleration time. So here's the equation. 3 seconds times 6,000 divided by 750 RPM times 4 poles gives us the ramp time, which is 6 seconds. So if we plug this into the VFD, we will get a 3-second ramp when we do this speed change. Pretty simple, actually. Okay, so where do we actually change the ramps in the VFD? Well, happily, those parameters are in the basic parameter set, that group of 15 parameters that are enabled by default. We set the acceleration ramp in parameter 1-03, and we set the deceleration ramp in parameter 1-04. By default, they're both set to 5 seconds, which is a fairly gentle acceleration. You probably noticed in our last session when we were ramping the motor up and down, it did take a certain amount of time. That's because we were using the default ramps. Now remember, this is 5 seconds for a 50 hertz speed change, but if you're in the United States, as I am, you probably have a 60 hertz motor. So when you put a 5-second ramp into these two parameters, the actual acceleration and deceleration time for a 60 hertz motor is 6 seconds. That's because you've got to go an extra 10 hertz while you're accelerating. So for example, if we have a 60 hertz 4-pole motor, it's going to take 6 seconds to accelerate from 0 to 1800 RPM, which is what its speed will be with a 4-pole motor at 60 hertz, and it will decelerate in that same time, 6 seconds to come down from 1800 RPM to 0 RPM. That is actually what you saw in the last session when I demonstrated my motor, because I have a 60 hertz motor. So do be aware there will be that difference there, but again, most of the time you're actually calculating what's going to happen, so you really don't have to think in terms of hertz if you don't wish. All right, I think it's time for a hands-on. You'll be a lot more comfortable with this once you've played with it. This is our first hands-on activity. Incidentally, I hope you took the time between the last session and this one to do a quick startup of your motor. So if you haven't done a quick startup yet, go ahead and do that because you will need your motor operable in order to do this hands-on. But once you've done that, your motor's functioning, let's go ahead and get into the hands-on. So here's what I'd like you to do. I would like you to accelerate your motor from 0 to 900 RPM in 1 second, and then decelerate it from 900 RPM to 0 RPM in 4 seconds. So this is a graph of what I'd like you to do. You can see you begin at full stop, 0 RPM, time goes by for a while, then you start the acceleration ramp, your speed goes up to 900 RPM, steadies out, and then it decelerates and comes to a full stop. It's going to take 1 second for the up ramp, and it's going to take 4 seconds for the down ramp. Now, of course, you're going to need to know how many poles your motor has in order to use the equation to calculate things out. I will be demonstrating this with a 4-pole motor, but if you have a different number, of course, your values will be different as well. Now, you may be wondering, how are you going to test this out when time has come to test it? Well, there's actually a very simple way to do this. What you need to do is get your speed set to 900 RPM first of all. So what you would do is press the start button on your motor, adjust the speed until you get it exactly at 900 RPM, use the up-down buttons, and then press the stop button. That will stop the VFD. However, the next time you press the start button, if you don't touch anything else, it will go back to the previous speed, in other words, 900 RPM. What you'll do is you'll get out a stopwatch, maybe the app on your smartphone. You'll press the start button, start the timer. When the acceleration completes, look at the time. And then to test the down ramp, you'll reset your stopwatch, press the stop button on the VFD, press the start button on your stopwatch, time it. When it comes to a full stop, hit stop on your stopwatch and see what time you had. And I think you'll discover, if you do everything right, that your ramps will behave just as you expect. All right, pause the video and do the hands-on. All right, time for a demonstration. I'm going to show you how this works on my VFD. If you don't have a demo unit, you can watch this, but if you did and you had some problems, hopefully this will help you out. First of all, we need to do a little math to work out our ramp values. So remember, we were accelerating our motor from 0 to 900 RPM in 1 second, and we're going to decelerate it from 900 RPM to 0 RPM in 4 seconds. Our speed change is actually going to be the same because we're doing the same speed change, it's just the direction that's different. So we take 900 RPM minus 0 RPM, and that gives us, unsurprisingly, 900 RPM is our speed change. Now we're going to need to use our equation twice because we have 2 different ramp times. We'll start by plugging in the acceleration value. We want this to take 1 second. So we take 1 second, we multiply it by 6,000 divided by 900 RPM times 4 poles, or whatever poles your motor has. Mine has 4. Now that gives us a ramp time of 1.66 seconds. Unfortunately, we're only allowed to enter 1 decimal place when we enter ramp values, so we have to round this. Now you might think we have to round it up to 1.7. That would give us a slightly longer ramp time. But you can actually round up or down, whatever works best for your application. So in this case, I'm going to be unconventional. I'm going to round it down and go with a slightly shorter ramp time in this case. And then we calculate that again with 4 seconds, and we get a time of 6.66 seconds. And in this case, I think I'll round up rather than round down, so that will give us a slightly longer ramp time, so we'll go up to 6.7 seconds. That is what we have to put into parameter 1-03 and 1-04. And if we do that speed change, we should get a 1 second acceleration and a 4 seconds deceleration. All right, so now we need to go into our VFD and set the ramps. So the first thing I'm going to do is disable my VFD. It's always smart to do this before you edit parameters, so I'll turn digital input 1 off. I don't have to put it into controller inhibit mode, I just should disable it. Now I enter parameter edit mode by holding down the navigate button for a few seconds. Okay, now I navigate to parameter 3, and I hit navigate, and I enter my first ramp value, 1.6. Hit navigate. All right, now I go to parameter 1-04, that's the deceleration ramp. I hit navigate, and I enter my time, 6.7 seconds. I hit navigate again to accept it. And that's it. I've now programmed my ramps. I hold down navigate to exit parameter edit mode, and we're all set to test. All right, the first thing I'm going to do now is turn digital input 1 on to enable my motor, and I'm going to press the start button. And now I'm going to use my up and down buttons to adjust my speed, so I'm going to get my speed tweaked to exactly 900 RPM. All right, now we're exactly at 900 RPM. I'm going to hit the stop button, bring my VFD to a halt, and I'm going to get out my smartphone and bring up a stopwatch app. What I'm going to do now is I'm going to start my stopwatch simultaneously with my VFD, so I'm going to press start on both of them at the same time. Here we go. All right, and you can see that took about 1 second to get up to 900 RPM. We're now going to reset the stopwatch and we're going to bring it to a halt by pressing the stop button, and we'll time the down ramp. Here we go. All right, and you can see that took the 4 seconds we were supposed to program in, so everything worked great. Pretty simple. All right, well, we're going to pause our discussion of ramps for a few minutes because to go further, we need to access the full parameter tree. As you recall from an earlier session, I mentioned that the complete parameter tree has 283 parameters. We have been dealing with what's called the basic parameters, which is a group of 15 that are necessary to do just a standard quick startup. But to have full control of our VFD, we need to access the entire parameter tree. So we're going to switch our VFD into what's called extended parameter mode. By default, most of the parameters are hidden. We're going to change that. And to do this, you go to parameter 1-14, which is in the basic parameters, and you enter a password which unlocks the full parameter tree. So what we need to do is we go to parameter 1-14 and we put a 201 in there. That is the default password which unlocks the complete parameter set. So once you do this, a whole bunch of parameters will become visible. The basic parameters, of course, there are just 15. They will remain visible. They're used for essential configuration. There are 191 extended parameters. And then there's a group of 77 parameters which you can't change. They're called the read-only parameters for that reason. They provide status information about the VFD. So once you put a 201 into parameter 1-14, all of these become visible, the full 283. Now, to make it easier to deal with all these parameters, they're divided up into 10 groups categorized by function. We'll be talking about what those are in just a minute. Now, we have already been working with parameters, but I've never really explained what the numbers mean, so now is a good time to cover that. All parameter names begin with the letter P, and then there's a number after them. That number is the group. This will be a number from 0 to 9. It identifies the group that the parameter is part of. The second number is the parameter itself. So I might say this is parameter 2-25. What that means is the parameter is in group number 2, and it's the 25th parameter within that group. All right, let's go through the groups just so you can know what they contain. Group 0 contains all the read-only parameters, which provide status information of the VFD. Group 1 contains the basic parameters, plus when you unlock the extended parameter tree, there will actually be a few extra. Group 2 contains things like set points, extended configuration information, and some parameters that deal with something called scaling. Group 3 contains the PID control parameters when you're operating the VFD in PID control mode, which is a fairly advanced mode. Group 4 contains parameters associated with the motor and with braking. Group 5 contains parameters associated with field bus and communications. Group 6 contains some specialized and advanced parameters used in special situations. Group 7 contains motor tuning parameters and electrical information. Group 8 contains advanced servo motor parameters that would be used if you're operating a servo motor in an advanced mode. And Group 9 contains parameters you set to configure the digital inputs. All right, so those are the extended parameters. Now, in our last session, I mentioned I would show you some shortcuts that would make it easier to work with parameters and to enter values. Since we're using the keypad at this stage, you've probably already recognized, since it has such a limited number of buttons, it is rather cumbersome to do certain things. These shortcuts actually make working with the keypad and working with parameters quite a bit easier. So here are 3 handy little shortcuts. The first one allows you to enter larger numbers, like, for example, the motor's nominal speed. Remember when we entered 1700 RPM, we had to hold that button down and then it accelerated increasingly the longer you held it down. A good alternative way is to enter the numbers digit by digit, and you can do this by pressing the Stop button and the Navigate button together. This allows you to select the individual digits and then just change them up and down. That's a lot simpler. If you want to go to the next parameter group, you would press Navigate plus the Up button, and if you would want to go to the previous parameter group, you would press Navigate and the Down button. And that would just make it a lot easier to switch between parameter groups and to edit numbers that are especially large. Okay, now that we've unlocked the extended parameter set, we can move on and talk about some additional ramp topics and also the subject of stopping the VFD. Now you may think, what's so complicated about stopping the VFD? Well, actually, the VFD is fairly sophisticated in how it handles stops. So let's jump in and talk about that now. The MOVITRAC LTP-B can stop the motor in 3 different ways: what we call coast to stop mode, ramp to stop mode, and rapid ramp to stop. Now, how do these differ? When the VFD is coasting to a stop, what it does, it switches off the output transistors, so basically it cuts power to the motor, and then the motor just coasts to a stop. Now, how long the motor takes to actually stop depends upon how it's loaded. If the motor has a very light load attached to it, it may stop very quickly as friction brings it to a halt. But if there's a very large load attached that has a fair amount of momentum, it's going to just keep running for quite a while. So when the VFD is in coast to stop mode, the stop time is actually unknown. You really can't predict how long it's going to take because it's load dependent. Now, on the other hand, ramp to stop is a little different. What it does is it decelerates the VFD deliberately using the ramp stored in parameter 1-04. Once it has completed the deceleration process, then it switches off the power transistors. So ramp to stop gives you a predictable stop time because it's using the deceleration ramp programmed in parameter 1-04. Rapid ramp to stop is basically the same idea, but it uses a separate ramp parameter. It decelerates using parameter 2-25, and that, of course, is why we have to unlock our extended parameter set. We wish to set this parameter, we have to go into a Group 2 section. Now, once it decelerates using the rapid stop ramp, it turns off the transistors, and again, you get a predictable stop time because it's using a deliberate deceleration ramp. I should mention as a side note, if the motor has a brake, it can be configured to engage after any of these 3 stops. In coast to stop mode, it can actually be quite useful because it can bring the drive to a stop very deliberately when the brake engages. So these are the 3 ways the MOVITRAC LTP-B can come to a halt. So how do we set up the stop mode? Well, parameter 1-05 in the basic parameters selects the stop mode. There are 2 possibilities that you can put into this parameter. If you put a 0 in there, it will ramp to a stop using the deceleration ramp in parameter 1-04. If you put a 1 in this parameter, the VFD will coast the motor to a stop. The rapid stop ramp is located in parameter 2-25 in the extended parameters, and it sets the rapid stop ramp's behavior. So by default, it's set to 2 seconds, but you can set it to whatever you like. Typically, the rapid stop ramp is meant for situations in which the motor needs to stop more rapidly than normal, for example, in a fault situation. So it's usually set to a fairly short value, but of course it doesn't really have to be. Let's talk about some events that can trigger a stop. There are actually quite a few things that can bring the VFD to a halt. Of course, the stop button on the front keypad is one. Input changes. If you're operating in terminal control mode, you can invoke one of several different kinds of stop events. If you're operating on a field bus, you can send several different stop commands over the field bus. Faults and errors can trigger stops as well. I'll mention here that stop behaviors may be fixed or configurable. In other words, some of these events will have only one kind of stop associated with them. Others, you can select what event you have, so it just depends. We'll talk about some of these as we go along through different sessions. Now, closely related to stops are power failure handling. What happens if the power fails to the VFD? Well, the MOVITRAC LTP-B can handle power failures in 3 different ways, and here they are. The first is called ride it out. The second is called coast to stop, which sounds familiar. And the third is rapid ramp to stop. Let's talk about how these 3 behaviors operate. The ride it out method is meant to handle very brief power interruptions where the power goes off for just a short time and then returns. In other words, kind of a power supply blip. Now, the way the system will behave if you've selected the ride it out method, it will reduce the motor speed, but it will attempt to keep running using stored energy in the VFD's filter capacitors. If the power outage is very brief, then this will work, and when the power returns, the VFD will return to normal speed. The problem with this method is that the outcome is unknown. If the power interruption is very brief, then you'll get away with ride it out. If the power outage is a long one, however, eventually the energy will be exhausted and the motor will stop, but you'll have no idea how long it will take or how it will tend to shut down. So this method carries some risks with it. Coast to stop is a slightly different strategy. It deliberately tries to stop the VFD. It does it by turning off the transistors, but then of course the motor is just going to freewheel until friction brings it to a stop. Now this at least will bring the VFD to a stop, but the stop time is unknown here just as it is with the regular coast to stop mode. Rapid ramp to a stop uses parameter 2-25 and it tries to bring the VFD to a very quick stop. So as soon as it detects a power failure, it decelerates using the rapid ramp parameter. It then turns off the transistors and hopefully everything shuts down cleanly before power fails. This at least has a predictable stop time. All three of these methods do have their place. It just depends what you're trying to do and how you want to handle a power failure. Now, where do you set up power failure handling? You do this in parameter 2-38 in the extended parameters. There are three possibilities. If you put a 0 in parameter 2-38, you get ride it out. 1 gives you coast to stop, and 2 gives you ramp using parameter 2-25. All right, well, that brings us to the end of session 3. In our next session, we're going to look at how to change to more advanced motor control modes. We'll look at VFC mode, which gives you better motor control than VF mode. And then we're going to do a major change. We're going to move away from using the keypad to parameterize our VFD, and we're going to look at how to use a PC and the engineering software LT Shell. So, lots of things to cover next time. See you then.